Okay, so let's start. So, in fact, was listed as organizer of this conference. Actually, my role is just to humanitarian one to help Anton to find a nice building which available 3 days. Yeah, and yeah, and also also Anton asked me to talk about something which it's not actually my active memory, this subject now, but I'll just give a very kind of short review what going on in string theory and how one can understand and generalize the structures. But first of all, I just want to say that there is a following simple question. One can calculate volume of unitary group with a natural with respect to measure related associated with natural Riemannian metric by trace of square is Killing metric. So it's some number you can calculate. It's actually a double gamma function. It's product of volumes of spheres. It's very easy to see. But then I can expand it as maybe a log of volume. Get a volume, and now consider volume to power inverse. Take a logarithm and try to expand as n goes to infinity. Yeah, so it's simple exercise with Stirling formula, but it's not gamma function, it's double gamma function. And you get something like some minus n square of log n minus square root of 2 pi log n. And then, maybe, oops, am I right? I hope so. And then you get series with g greater than 2, earlier characteristic of modulus space of curves without marked points to power n to power 2 minus 2g. Yeah, that's one knows from Harrer and Zagier. It's Bernoulli number divided by something, by 2g minus 1, 2g minus 2. This also one can calculate. Yeah, so it's one can really easily check this. It's really not a big deal, but the question, can we make intrinsic proof of it? And at the moment, it's not the case. Yeah, so I think it will be a really good goal to find an intrinsic explanation. Yeah, so it's actually part of general frame patterns that if consider integral of space by n matrices, take logarithm and expand to get some high genus expansion, which we know in some few class of kind of integrable situations. But in general, there should be some inner explanation. So I will speak about kind of the following thing. There is A model will be B model and categorical language. So what is A model? Suppose we get a compact, for a moment, symplectic manifold, and then there are Gromov-Witten invariants, which are virtual fundamental classes of modulus space of stable maps, XD, which are in cohomology of certain degree of x to power n times mg n bar, irrational coefficients. D here is a degree of a curve, which I interpret as just integral homology class. And this dimension is calculated through some formula. It's half of real dimension of x minus 3 times genus of my curve minus 1 minus genus plus number of marked points and plus integral first chain class of tangent bundle over homology class D. So it's a sum. There are such classes, and it's well known that the whole thing can be organized to cohomological field theory. So you have vector space H equal to just cohomology of X, and you get a map from H to power m to cohomology of mj n bar. You take the sum of all these things with weight with powers q to power d. It's kind of depending on formal parameters qi, where I ranks from 1 to what's it called, R, which is rank of second homology. You calculate, you consider kind of qi to powers integral over corresponding basis curve representative of these cohomology classes over divisor D. It takes some of all possible degrees. So you get a cohomological field theory depending on some parameters. Now there is a description of what going to Bay model if it exists. And B model story is not so obvious, because what was originally story, if genus is equal to 0, all this reduced to story about variation of hot structures. Sorry? I lived? Okay. Exponential hot structures, at least part of this genus 0 invariance. Namely, if a mere object exists, it should be an algebraic variety of the same complex algebraic variety of the same dimension as X, with holomorphic with algebraic volume element. Let's call this wall, and a potential. We just map to, which is again polynomial map, such that W should be proper map. And then again, this will be object dual to X in symplectic form. It also will depend on R parameter, where R was and one can identify parameters one with another, such that logarithm of qi from I equal to 1 to R will be ratio of two integral. You integrate exponent of W times volume over certain cycles and divide by integral of exponent of W of volume of gamma 0, gamma 1, gamma R are some integer chains, not necessarily close such chains that you can integrate exponent of potentials. They go to infinity to direction when exponent decay. Maybe I should put multiply by 2 pi square root of minus 1 here. So that one have this Ri, this coordinates will be kind of transcendental coordinates on moduli space of these varieties with potentials, and one calculate different integrals. One can translate to structure about genus 0 part of invariance. But it's but for high genus, it's kind of extremely painful. So going from high genus, how to describe in terms of this B model. It's not really clear at all. Yeah, let's consider some kind of most central case in the whole story. You just look on this equation, kind of central case. When dimension of x is 6, or complex dimension is 3, and first Chern class is 0. Then in this case, what you get essentially for each, then it means that curves of any degree of any genus without mark point should form a zero-dimensional moduli space, and so you should count them again. You just get those numbers. And all these equations that we get homological field theory became completely vacuous in this case. The whole story is defined by just all information will be some series fg, where g greater than 0, will be functions in R variables, which are expanded at some formal power series, and for small genus will be logarithm corrections. Yeah. So F0 it's kind of understood through variation of hot structure, but for high genus, there was a model proposed by physicists, kind of Feynman integral, proposed by Bershadsky, Chikoty, Aguri, Waffa. It's called Kadeiro-Spencer theory. What is Kadeiro-Spencer theory? One can make a very general class of Feynman integrals with the following form. Suppose you get a differential graded Lie algebra in degree, which sits in degrees 0, 1, 2, and 3. Just 4 degrees. And you have a differential of degree plus 1, and also suppose you get a pairing. Which is kind of non-degenerate. Why I put parentheses? Because the algebra will be infinite dimensional. And compatible with a bracket. So A, B, C. These are some causal, maybe no causal rule signs. It's kind of. Okay, it's and compatible with differential. Then one can write Chern-Simons functional. A second, somebody's trying to. One can write Chern-Simons functional on kind of G1. Say, you integrate pairing gamma with d gamma plus maybe over 2 and plus gamma over 6. You consider Chern-Simons of gamma is this pairing, and then you can try to integrate exponent of Chern-Simons functional modular gauge transformation by degree 0. Yeah, so Kadeiro-Spencer theory is a particular example for some Lie algebra, and what is Lie algebra is the following. You consider D-bar forms on Calabi-Yau threefold, which will be mirror-dual. Why? Potential will be 0 in this case. You consider D-bar form with values in divergence-free holomorphic vector fields. So locally you consider tensor product of functions and forms in Z-bar, depending on Z-bar, and holomorphic vector fields in Z with 0 divergence. Yeah, then this differential, there is a slight problem with the pairing, because if you have two forms, let's say A and B, there are two forms which A belongs, let's say, 0I form, and this gives 0 part of tangent bundle, and B belongs to 0, 3 minus I form. one can't really multiply because the product will be 0-3 forms, and then it should do something with holomorphic vector fields. But because it's divergence free, it should be one can substitute to form. It says it's d bar closed to form 2 comma anything form. Holomorphic vector fields you contract with holomorphic polymer element to get 2 form in holomorphic direction. Because d bar closed, you write it's kind of you can write d minus 1 of this. You get one form in holomorphic direction. So so what you do essentially integrate. You replace this by forms. And the pairing AB will be integral of d inverse of A which B, because we say it's if it's closed, it should be total derivative of something. Yeah, there is some slight problem along some finite dimensional space with this definition, but you get some field theory, and this guy's Birshovsky category suppose that if you start to calculate exponent of Chern-Simons action for this theory divided by h bar and take logarithm expansion, you should get h to power 2 minus 2g minus 2 times fg. Yeah, unfortunately, this thing it's very ill-defined. All Feynman integrals diverge. But also, there's really no way to canonically regularize it. So it's extremely bad shape. Yeah. So, but it gives some idea about a holomorphic anomaly equation. In holomorphic anomaly equation, it's kind of very close relative to what Maxime Kazaryan explained just before. Essentially, it says that. He didn't actually explain what is holomorphic anomaly equation. He said that you get some infinite dimensional space, you get some decomposition to Lagrangian subspace and functions, so it gives a Lagrangian submanifold. And then you try to quantize this Lagrangian submanifold to get a vector and a Weyl representation. And this holomorphic anomaly equation means that if you kind of change parameters of your series, this vector stays the same. So it's more or less the same as these equations which he explained. Yeah. So now what with categories? Yeah, in a sense, it's a way to regularize this BCOV and in kind of proof that geometric series which come from symplectic geometry coincide with series coming from complex geometry. Yeah, so there was a project which was started more than 10 years ago. Was a project which is not yet in completely satisfactory shape, which says the following. So how we encode this Gromov-Witten invariance through some algebraic data. So for simply, the algebraic data will be the following. It will be a finite collection of complex numbers, which can be thought here as the critical values of W in this example. It could be, yeah, in principle, this potential should be 0. It should be just one number 0. Then for each number, you get some algebraic gadget, which is called a smooth compact infinity category with Calabi-Yau structure. So the category Ci in this example, with potential is that actually, let me explain. It's the critical values of W, or it's the same as eigenvalues of operator of quantum product by first-chain class. Yeah, so one can make a comparison between A and B model. And so you get this infinity category. The category will be the following. It will be, if one try to define Foucault category for manifold, consists of Lagrangian manifold, Lagrangian manifolds will be some kind of abstraction to existence of the object in the category, and one can shift by kind of by identity multiplied by some eigenvalue, get something non-empty. So there are not one Foucault category, but several Foucault categories corresponding to eigenvalues. And here are the things called category of matrix factorizations. And so it's some algebraic gadget, smooth compact infinity category. Whatever it is, one can say it's some finite dimensional Z supervector space, if one choose some generator, plus bunch of tensors, of some tensors, actually infinite bunch of tensors satisfying some equation, but modulo gauge equivalence, you get finite number of parameters. So it thinks it's kind of algebraizable number of parameters. So in principle, one should have, again, some kind of mathematical programs working effectively with this stuff. Like in Maxime Kazaran's talk, but it's completely different calculus. Yeah, the Calabi-Yau structure, it's also, one can formulate in this way. Calabi-Yau structure is the following gadget. For each category, we can associate something called negative cyclic homology. And this is actually a module over Taylor series in one variable, which in this subject is variable denoted by letter U. It's come from kind of non-commutative geometry and Kohn operator and so on. Yeah, and the whole thing seems to be, work when this model is actually free of finite rank. Yeah, so you get vector bundle. And this Calabi-Yau structure is a section of line bundle with vanish at zero, and derivative should be invertible element, more or less in the same sense as Maxime explained here. So it will be some invertibility property. Now it will be Calabi-Yau structure, and then one can make. But this thing, the category's Calabi-Yau structure gives not much. Each individual category gives a functor from its homology, or there is some Hochschild homology of Hn at U equal to 0 to power n, maps to, for each category, Ci. Get fiber. It maps to cohomology of modular space of curves, but without bar. Without bar and with arrow. Arrow, it means I consider stable curves with tangent direction at each point. Yeah, this is purely algebraic game, and how it roughly constructed, one can encode this infinity category sequence of some cyclic tensors, and the cyclic tensors you put, make from them invariants according to ribbon graphs, and it will be cochains in the ribbon graphs. Yeah. So that's basically it's pure algebraic construction. Yeah, and the plan to prove this whole thing was that this pure algebraic construction one can specify for Foucault category, identify with Gromov-Witten invariant, or specify with complex manifold and satisfy some kind of regularization of this Kader-Spencer theory. Yeah, so there's a problem. There's an arrow and there's no bar. And to go from, to replace mgn head by mgn bar, one need make an additional choice. Choice is the following. Yeah, actually, I forgot to say they get a vector bundle with flat connection on and with regular singularity for each category. And the choice is the following. We consider direct sum of Hn of this category Ci multiplied by kind of one-dimensional bundle with connection, which I denote by exponent of Wi divided by U. So you consider connection whose in one-dimensional function whose solution is exponent. You take direct sum, you get a bundle with flat connection with second-order pole on a formal disk, and identify these things as formal neighborhood at infinity at 0 of a connection of the following type. This will be du du, kind of trivial bundle. And connection is consists of given by two matrices.
Maxim, but Hn you denote Cauchy chains or Cauchy complex. So what is Hn?
Negative cyclic homology.
Hn?
Oh, negative. Hn.
Okay, and the other, and the Ci?
Ci of category. Okay.
Okay.
Yeah. Yeah, so it's a direct sum, get some formal guy, and now you just want to make some gauge transformation to get just two matrices, A and B. Yeah, there will be, again, finitely many parameters how to do it. And if you do it, then you extend your theory to mjn bar. If you do it different way, you extend in different way. And these different choices are related by this given tile group. Yeah, so it's all was very nice, and there was some kind of account of this story by Kevin Costello, but somehow we also communicated with him a lot, and there was some kind of final problem. We cannot really make it to the closed formula, and the reason is completely idiotic. It's this is pure combinatorial equation. How we can make moduli space. This trivialization should give some tool to go to modulus to mjn bar, and eventually we construct some cell complex which homotopy equivalent to mjn bar. And for example, we want to calculate integral of fundamental class like fg. And the problem is this complex is of infinite dimensional. It's homotopy equivalent to mjn bar. It's infinite dimensional, and I don't know any good, nice representative of the fundamental class. If it will be representative, it will be closed formula, and then we can kind of state of physics is that the problem is solved. Yeah, what is? Eventually, yeah. So it's really kind of some stupid stumbling block, but that's why it's not really yet kind of formal, official kind of picture of the story. Yeah. So that was a picture about. Closed Gromov-Witten invariants. Now I want to say a few words about just before going on, I want to mention also some important thing. There was a proposal by Sergei Barannikov and it's slightly different linear algebra. So instead of having a infinity algebra and all this data, he has a vector space, which is also infinity algebra, finite dimensional vector space, and a lot of elements in symmetric powers of the cyclic powers of my vector space, satisfying some. You get tensors in such things, satisfying some, again, Maurer-Cartan equation, and then gives the classes in homology of mg and bar. Now I should put prime, and prime is it's a contraction of mgn bar. Namely, if you have on your stable curve, you get components which are free, which don't have marked points. You ignore complex structure on such guys. Yeah, that's actually was a space which somehow appeared intermediate in my proof of this area function of Witten conjecture, some intermediate space. And the classes are here, not on mgn bar. So it's not terribly perfect story. One should really remove this prime. And it's not clear how these parameters are related to these parameters, at least not to me.
Why not to pull them back?
You can just take
Why
the
not
image.
to pull them back to the usual?
No. Maybe get because it's the elements in homology.
In cogomology too also.
Also, okay, good, okay. But whether they will satisfy the axiomatics, it's not, probably not, I'm afraid. Yeah, okay, so it was about closed invariant, and now there's a pretty interesting story about open invariants, open closed GV invariants. And let me concentrate on the case of Calabi-Yau threefolds. Yeah, so you see that it's kind of case which is completely kind of perpendicular to this semi-simple case which Maxime explained. So the freedom is huge. You get plenty of functions and no equation of chemical them. Oh, just before going on, I want to say that's a really kind of corollary from all this picture. For Calabi-Yau threefolds, one can this gauge choices, one can make it pretty explicit in geometric situation. If you get Y Calabi-Yau threefold and you have a choice of volume element, it's a variety, but I should choose the volume element, and also I choose a subspace. This was denoted something called orthogonal space L or V, I forgot which you complementary space you do. L, yeah. And you choose L in H3 YC, the RAM, complementary to terms of Hodge filtration, to H30 plus H21, which is actually called F2 of H3. It's Hodge filtration. Then if you get such things, then the whole story, all these gauge choices will be automatically made, and then you get number Fg. For any G. And maybe at least 2. And this number satisfies some equation if you rotate L. But in particular, what you can see is that this Fg are functions on some algebraic variety. Because, so it's G, it's kind of algebraic function on moduli spaces of this Y, volume, and L. This is algebraic variety. And it's corresponds to really kind of algebraic parameters for categories of coherent shifts. And for example, if Y is mirror dual to quintics, then Y depends on one parameter, volume depends on one parameter, and this Lagrange subspace in 4-dimensional space depends on 3 parameters. You get 5-dimensional algebraic variety. And Fg will be think on this, and Fg, which you can see in actual Gromf-Witten invariance, is obtained by restriction to some transcendental submanifold here. But so we see that they're algebraically dependent. So if you consider series coming from geometric function, there will be polynomials in first 5 series. And Yau and company checked it. And but up to now, and also Albert Clem calculated maybe first 50 these polynomials, but because this technology is still not available, so he used some kind of boundary data, but for very large genes they are not sufficient. You get some freedom Gromov anomaly equation does really determine two things completely. Yeah, so theoretically the answer exists, but in practical terms it's not yet here.
But what is is there any definition of these FGs except?
Yeah, no, that's its only definition. Yeah, yeah, essentially, Costello has some paper when he have a definition of G without going to constructing homological field theory at all. Yeah, so but it's very hard to extract any number. So it's now it's about open-closed Gromov-Peterson invariants. Suppose my Calabi-Yau threefold is a symplectic manifold, contains three-dimensional Lagrangian submanifold, which I'm afraid maybe I assume it will be a sphere. So yeah, so suppose I get a sphere, Lagrangian sphere sitting in my three-dimensional Lagrangian manifold. Then one can try to count the following guys. One can count, make a genetic series FGH, number FGH. It will be sum of degrees, q to power of degree. And here we get a number of curves of genus G and H holes, and boundary belongs to this three-dimensional sphere. Yeah. Now, strictly speaking, it's not really well-defined problem in normative geometry because get boundary modular space with real boundary. But then there was suggestion by Vito Iacovino how to regularize the problem. One considers such curves and also draw something like roughly gradient lines on underlying sphere connecting points. Yeah, so just add a little bit of, yeah, so roughly speaking, one can consider maybe degenerate surfaces which consist of several components, and there will be some gradient, it's a bit long story, some gradient line connecting point on one circle to another circle in the three. And then the whole guy will have no boundary. So it's really well-defined numbers for homological spheres. Yeah, so get, and then if you can make parameter, it looks like we get new variable to raise to power h. Yeah, and what is this new variable? And then there was a picture by physicists of a conifold transition. If you get a sphere in Calabi-Yau threefold, then I can construct a new family, one parameter family, and one parameter will be responsible for this H of symplectic manifolds. Namely, you do the following. You consider neighborhood of the sphere. Neighborhood looks like a cotangent bundle to a sphere. And the things you can also identify with complex quadric sitting in C4. Then this complex quadric you can degenerate. You get kind of singular complex variety. So it means I contract S3 to a point. But now we can smoothen the complex geometry by make a kind of blow up. But only get kind of small blow up. You glue inside CP1 instead of, if you the full blow up you glue CP1 cross CP1, but you just contract one, so you glue CP1. So in topological you contract and deform, you get S2. And what you get total space of two-dimensional bundle over CP1. Yeah, so you replace three-dimensional sphere by two-dimensional sphere. And now in this symplectic manifold has extra new homology class of the sphere. And then it means that it has more parameters as symplectic manifold. You can change symplectic structure adding parameters corresponding to the thing. And the claim is that closed Gromov-Witten invariance for kind of x maybe tilde, for x tilde equal to open closed for original for x and this three-dimensional sphere. And morally it's kind of clear, because if you consider this curve, then after this procedure you get a curve and have some copies of CP1 added to this curve. Yeah. Yes. So before you get curve plus three-dimensional sphere, which is not really anything reasonable, but after this translation, you get a curve and copies of CP1. Yeah, the same one can do with several S3s, and several disjoint spheres. Then I get more parameters and get things depending on more parameters. Yeah. Now I want to say what it corresponds in B model in category language model. In B model, it's actually opposite situation. Suppose you get Calabi-Yau threefold, and it contains what's called -1, a rigid rational curve. Which is rational curve with normal bundle O-1 plus O-1. So typical rational curve should be this -1, -1. If you get this curve, you can construct, then you get a one parameter family of new Calabi-Yau threefolds of Calabi-Yau, Y tilde. And how it's obtained, you construct a curve to a point, and then try to smoothen it. Yeah, so it's exactly this procedure, but in sense going opposite way. So and you don't blow up now. You construct the point, you get things, but now try to smoothen it. So go from singular guy to this quadratic singularity. This epsilon will be a parameter for deformation. Yeah, So that's the story, and also in categories it's also very nice. Namely, you can see the category of coherent sheaves on my Calabi-Yau variety. That's abstract category, which could be Foucault category, and then this curve C, O of C, is its object of this category, this curve C, and it's a spherical object. So it means that X group from this object to itself are cohomology of three-dimensional sphere. Then this contracting to curve to a point, it makes singular variety, and perfect complexes on the singular variety, it's a quotient category. Oh, it's not a quotient category, sorry. It's semi-orthogonal complement to O. Objects E, such X from E to this of the spherical object is 0. Actually, it's perfect complexes on this category. It's a kind of full subcategory. It's kind of singular variety. and you can try to deform it using as a category, triangulated category, and you get this new family. Yeah, this thing's actually not really yet done. Yeah, so one can guess the whole thing behave nicely. So you get any three-dimensional Calabi-Yau category, get spherical object, and you get new one-parameter family. Yeah, and now, and also this thing should be kind of a theorem, yeah, that this open-closed invariants are closed in Gromov-Fitch invariants. So one should find some kind of formulation what is open-closed Gromov-Fitch invariants in two different frameworks, kind of in B model, in a more abstract categorical model. So, in meaning of open-closed invariants in B model is the following. In B model is integral of exponent of Chern-Simons divided over H bar of over what? Over for Lie algebra will be another Lie algebra, will be BD bar forms. Actually, with values where? Yeah, in general, one get this open-closed invariants defined for B model and plus any, let's say, coherent shifts or coherent shift or holomorphic bundle, which is spherical object. Could be a rigid holomorphic bundle. Yeah, so consider D-bar forms with values and endomorphisms of this bundle. And then this that will be another quantum field theory, holomorphic Chern-Simons. Yeah, there is actually a much better situation here. With holomorphic Chern-Simons, you also get some Feynman diagrams, so expansion, and the whole thing is divergent as for Kaday-Spencer theory, but there is canonical regularization of all of Feynman diagrams. So the whole thing is well defined. And in pure categorical I think it should reduce to matrix integral. That's it. And categorically, you calculate the matrix integral. Yeah, and here there's a really interesting point here. The whole thing exists. There's also kind of this additional choice which I made. This gauging, this gauge choice should kind of affect this matrix integral as well, because it's how we define what are stable curves. And so the again thing which is not yet really done, so one can make a guess. To define Chern-Simons integral in algebraic situation, algebraic model, one needs a measure on space of objects of your category or my bundles. Yeah. And I need a way to define measure. And it's not clear at all, because this Calabi-Yau structure gives what's called minus one shifted symplectic structure on moduli space of object. What does it mean? That if consider deformation of any roughly considered deformation of any holomorphic bundle or kind of more general object with category on the tangent space will be X group shifted by 1 and get this Calabi pairing gives you symplectic structure of degree -1 on the super space. And then one, in this situation, one get a also Chern-Simons function will be some function whose commutator with itself equal to 0. But for this odd symplectic structure, there is no canonical volume element, unlike even case. And it's additional data. So we have kind of classical master equation that things commute with itself, but there's no way to write what is Laplacian, things is equal to 0. It doesn't make sense without volume element. And volume element is something not for free. And I think it's really comes from this additional trivialization of negative cyclic homology, which appear and this is not yet from identification. Negative cyclic homology should be Hochschild homology series in U. And we should trivialize this line vector bundle. Yeah, that's actually interesting algebraic gadget to translate everything to algebra, and then we can see that we can translate infinite dimensional integrals as Feynman things to some game with tensors. Yeah, so it's that's what's going on. Yeah, and in fact, if you have yeah, you see, I write it if it'll be holomorphic bundle, you'll get kind of 6-dimensional field theory. But if it's coherent shift supported outside in a curve, it looks really 2-dimensional theory. Because this curve could be contracted to a point, it's even 0-dimensional series. So it should be reduced to matrix integrals on the nose stuff. Yeah, so in fact, this holomorphic Chern-Simons theory, depending on dimension of support of your sheaf, will be quantum field series in different dimensions. 0, 2, 4, and 6. Yeah, so you get this holomorphic Chern-Simons gives kind of quantum field theory in dimensions 0, 2, 4, and 6. Actually, I want to say that there's one important thing. In this open-closed things, I have 2 indices, genus and whole, and here I should get also 2 parameters. I get h bar, but also I consider n copies of my vector bundle. Yeah, so I should so there are parameters h bar and n, and genus and h. They correspond to each. There are 2 parameters here and there. So there is some kind of Laplace transform going here.
So when you say QFT, you mean 2-dimensional topological quantum field?
No, not quantum fields, not topological. Yeah. No, there will be some supersymmetry here, so there are tools to calculate stuff, but it's not topological. Yeah. In principle, in some special cases, one can write things in A model. There was one point here. Essentially, yeah, all nice story, I have to say, but up to now there is really no example of compact Calabi-Yau threefold where we know these numbers. Yeah, so it's all because of all things it's not fully done as this algebraic translation. Yeah, so it's at least not in the sense that it can show numbers to physicists. Yeah, so this and almost all things which do physicists explicitly, it's some kind of limit case. Say you consider non-compact symplectic manifolds. So consider non-compact symplectic manifold, which can be said the following: it's XV. It sits in some compact symplectic manifold when we have divisor at infinity should be semi-ample. So it means that intersection with any curve would be non-negative. Then, so symplectic manifolds from which the whole story can work usually realized as complement to divisor. And then consider GV invariance for x bar with omega and plus add some parameter kind of 1 over epsilon times the class of divisor to infinity. Usually positive non-negative class, so it makes sense. And when epsilon goes to 0, you can go to the limit and only curves which do not intersect the divisor to infinity. So in a sense, open manifolds are kind of limits of closed guys from which there is a good picture. Unfortunately, I don't know good algebraic translation of what is a non-compact manifold. Yeah, so it's things which is still missing. But here there are plenty of calculation were done, and in particular, one can apply to the case when X is a cotangent bundle to some three-dimensional manifold M3, which is on a situation. And then this open Gromov-Witten invariance in the story, it means that you calculate Chernow-Simons theory, real Chernow-Simons theory, but for UN bundles, the n goes to infinity, you expand in n, and divided by h bar. So you get two parameters, n h bar, and in particular this question which I think about the volume, it should be some kind of limiting case for case of three-dimensional sphere. Yeah, so the explanation should go through this thing. Yeah, so one can get also three-dimensional theory as one of degenerate cases. Yeah, okay, and finally, I want to see what is the role of topological recursion from this perspective. Yeah, and topological recursion, when you make generating series, it will be series in infinitely many variables. In principle, this whole stuff also works in very general situation, like at gravitational descendants, but what will be geometric meaning? Series in infinitely many variables. In variables, things like T1, T2, maybe P1, P2. Infinitely many variables. And how are you going to try to see these variables? The picture is that Lagrangian manifold, which you consider now, is not one connected, but it has first homology. Suppose it's my Lagrangian manifold is 1 cross R2. So it's some kind of thing like this. And then if you get, now you count your manifolds with boundary, each boundary components will wrap some number of times. And one can see that number of times will be, if it's in some situations could be kind of always positive. So this number of times will be I times wrap. Then it's supposed to weight pi to this thing. Yeah. So it's a way how to introduce infinitely many variables. And what does it mean? This infinitely many variables. Yeah, so this another way to arrange the whole thing was to have symmetric functions. You can have functions, something like tjn of n variables, for each n symmetric in these variables, and when you expand, you get some Taylor coefficients which will be wrapping thing, and so the way to do it is the following: this variable z1, zn can be thought as parameters of objects in Foucault category. Because when you have this S1 cross R2, one can put on this, it's Lagrange manifold, but also one can modify it, put rank 1 local system, which depends on one parameter. And my guess is that these functions which appear in functions of many, many variables which appear, the I runs through some algebraic varieties, some kind of algebraic curves. These algebraic curves parameterize objects in Foucault category, and that again should be kind of translated to some pure algebraic game. But in principle, one can go to more examples. For example, one consider things with two generators of first homology, and it will be instead of curves, we get surfaces and so on. Yes. And pretty abstractly, of course, in real life, in principle, you can get Lagrange manifolds with arbitrary rank of H1. So you get a huge family of object of categories. And my guess it's again chance. So you get some object depending on the I. And my guess it's what you calculate here to calculate Chern-Simons exponent of integral of Chern-Simons near EZ1 plus PZN. Yeah, that's maybe how one can really see this stuff. Okay, thank you.
In Foucault category, there are no poles.
Sorry?
Usually, for objects in Foucault category, there are no poles.
Poles?
Yes, because the functions which we are studying, they have poles on diagonals.
But Holmes, but here there's something singular, because Holmes between if you have objects depending on parameter, then Holmes really jump on diagonal. Identity morphism disappears. Yes, Holmes are between different objects. No, but you consider endomorphism of this guy. This dimension of cohomology jumps when points start to coincide. No, just that's it. Yeah.
Question. So on that point, so if you take Carbia as a tangent bundle and so your Chern-Simons is based on the Lier Chern-Simons theory.
Yeah.
And my question is, what happens if you take a sort of generic Carbia so that similar direction occurs?
No. If you make general Calabi-Yau threefold, I've considered general Lagrangian manifold sitting in Calabi-Yau threefold, like 6, then the Chern-Simons will be, in sense, one can write formal stuff. This Lagrange manifold will contain infinitely many loops, which will be boundaries of holomorphic disks, or maybe collection of loops with boundaries of curves. It will be isolated, plenty of loops, and you kind of modify Chern-Simons section by adding, consider connections which are not flat but have some defect, and so it's pretty complicated story. Yeah, so it's can be said it's kind of local functional. It has some information coming from ambient manifold. Yeah, one can write some action in this way. So.